Hi students, in this session we will discuss about Norton's theorem, and first of all we can state Norton's theorem. Norton's theorem states that any two-terminal linear network with current source, voltage sources and resistances can be replaced by an equivalent circuit consisting of a current source in parallel with a resistance. And the value of the current source is the short circuit current between the two terminals of the network, and the resistance is the equivalent resistance measured between the terminals of the network with all the energy sources are replaced by the internal resistance. And the Norton's equivalent circuit is shown in the figure, that is IN is a current source, RN is the parallel resistance, RL is the load resistance. So if we are given a complex network, we can represent that complex network by a simple network with a current source and a parallel resistance. So Norton's theorem state about how Norton's theorem states that how we can convert a complex network into a simple network. And here the Norton's theorem, in the case of Thevenin's theorem, we have similarly converted a complex network into another network that is containing a voltage source VTH and a series resistance RTH. And here we are converting the complex network into a current source and a parallel resistance. So the steps are, it is stating that a complex network that is a linear network and that contains current sources and voltage sources and resistance, and that can be replaced by an equivalent circuit consisting of current source with current source in parallel with a resistance, that is shown in the figure. And the value of the current source can be obtained by short circuiting the output terminals. That means if there is a load resistance, we have to short circuit that load resistance, and the current through that load resistance, that short circuit will give the Norton's current source IN. In the Thevenin's theorem, what we are doing is we will replace the load resistance by open circuit, but here in the case of Norton's theorem, we are replacing the load resistance by a short circuit, and the short circuit current will be the Norton's current IN. And in the case of Thevenin's theorem, we have find out the equivalent resistance by replacing the load resistance, and also by replacing the voltage sources by short circuit and current source by open circuit. Similarly, we got in the case of Norton's theorem, we are replacing the load resistance, and also we are replacing the voltage sources by short circuit and current sources by open circuit. Then we will get the Norton's equivalent resistance. That means the way we are getting the Norton's equivalent resistance and Thevenin's equivalent resistance is the same, but the difference is between the finding of between the way we get VTH and IN. In the case of VTH, we are placing an open circuit instead of load resistance, but in the case of Norton's theorem, we are placing a short circuit instead of load resistance, and we will find out the short circuit current, and that short circuit current will give the Norton's current source. Okay. So the steps for finding current through a particular branch in the case of Norton's theorem is that first step is, first we have to replace the load impedance by a short circuit. That is the first step. And in the second step, then we can find the short circuit current IN, that is flowing through the short circuit placed in the place of load resistance. And in the third step, we will remove the load impedance from the circuit by an open circuit and replace all the voltage sources with their internal impedance. That means they are replaced by a short circuit and current sources are replaced with the open circuit. And then find equivalent resistance. In the case of AC circuit, it is represented by Zn, and in the case of DC circuit, it is represented in terms of Rn. And that means it is equivalent impedance across the open terminals. And in the fourth step, we can draw the Norton's equivalent circuit by drawing IN parallel to Zn and ZL. And then we can find out the load current by using the equation IL will be equal to IN into Zn divided by Zn plus ZL. This is the case of steps used for finding out current through a particular branch. അതായത് നോർട്ടൺസ് തിയറം വെച്ചിട്ട് എങ്ങനെയാണ് നമ്മളൊരു ബ്രാഞ്ചിലൂടെയുള്ള കറണ്ട് കണ്ടുപിടിക്കുന്നതെന്ന് വെച്ച് കഴിഞ്ഞാൽ നമുക്ക് ഏത് ബ്രാഞ്ചിലൂടെയുള്ള കറണ്ടാണോ കണ്ടുപിടിക്കേണ്ടത് അതിനെ ലോഡ് ഇമ്പിഡൻസ് ആയിട്ട് കണക്കാക്കുക. ആ ലോഡ് ഇമ്പിഡൻസിനെ ഫസ്റ്റ് സ്റ്റെപ്പിൽ തന്നെ ഷോർട്ട് സർക്യൂട്ട് വെച്ച് റീപ്ലേസ് ചെയ്യുക. ആ ലോഡ് ഇമ്പിഡൻസ് മാറ്റിയിട്ട് അതിന് പകരം അവിടെ ഒരു ഷോർട്ട് സർക്യൂട്ട് വരയ്ക്കുക. അപ്പോൾ ആ ഷോർട്ട് സർക്യൂട്ടിലൂടെ പോകുന്ന കറണ്ടാണ് നോർട്ടൺസ് കറണ്ട് എന്ന് പറയുന്നത്. അപ്പോൾ അതാണ് IN. IN നമുക്ക് കിട്ടിക്കഴിഞ്ഞാൽ നെക്സ്റ്റ് സ്റ്റെപ്പിൽ നമ്മൾ എന്താ ചെയ്യണം, RN ആണ് ഫൈൻഡ് ഔട്ട് ചെയ്യേണ്ടത്. RN ഫൈൻഡ് ഔട്ട് ചെയ്യുന്ന സ്റ്റെപ്പ് എന്ന് പറഞ്ഞാൽ തെവെനിൻസ് തിയറത്തിൽ RTH ഫൈൻഡ് ഔട്ട് ചെയ്യുന്നത് പോലെ തന്നെയാണ്. അതായത് ലോഡ് ഇമ്പിഡൻസിന് RTHനെ റീപ്ലേസ് ചെയ്തിട്ട് അവിടെ ഓപ്പൺ സർക്യൂട്ട് കാണിക്കും. ആ ഓപ്പൺ സർക്യൂട്ടിന് അക്രോസ് ഉള്ള വോൾട്ടേജ് ആണ് റെസിസ്റ്റൻസ് ആണ് RN എന്ന് പറയുന്നത്. അത് തന്നെയായിരുന്നു RTH. അപ്പോൾ അങ്ങനെ RTH കണ്ടുപിടിക്കാൻ വേണ്ടിയിട്ട് അല്ലെങ്കിൽ RN കണ്ടുപിടിക്കാൻ വേണ്ടിയിട്ട് നമ്മൾ വോൾട്ടേജ് സോഴ്സിനെ ഷോർട്ട് സർക്യൂട്ട് വെച്ചിട്ട് റീപ്ലേസ് ചെയ്യണം, കറണ്ട് സോഴ്സിനെ ഓപ്പൺ സർക്യൂട്ട് വെച്ചിട്ട് റീപ്ലേസ് ചെയ്യണം. നമുക്ക് INഉം RNഉം കിട്ടിക്കഴിഞ്ഞാൽ പിന്നെ നമുക്ക് നോർട്ടൺസ് ഇക്വാലന്റ് സർക്യൂട്ട് വരക്കാം. സപ്പോസ് ലോഡ് റെസിസ്റ്റൻസ് തന്നിട്ടുണ്ടെങ്കിൽ ലോഡ് റെസിസ്റ്റൻസ് ആ RNന് പാരലായിട്ട് വരക്കാം. ലോഡ് റെസിസ്റ്റൻസ് ഇല്ല എങ്കിൽ ആ ടെർമിനൽസ് ഓപ്പൺ ആക്കി വെക്കാം. ഒരു ലോഡ് റെസിസ്റ്റൻസ് തന്നിട്ട് അതിലൂടെയുള്ള കറണ്ട് കണ്ടുപിടിക്കാനാണ് പറയുന്നതെങ്കിൽ നമ്മൾ യൂസ് ചെയ്യേണ്ട ഇക്വേഷൻ IL = IN × Zn / Zn + ZL. ഇതാണ് നമ്മൾ യൂസ് ചെയ്യേണ്ട ഇക്വേഷൻ. ഇത് സിമിലർ ടു തെവെനിൻസ് തിയറം ആണ് നോർട്ടൺസ് തിയറം എന്ന് പറയുന്നത്. തെവെനിൻസ് തിയറത്തിൽ വോൾട്ടേജ് VTH ആണ് കണ്ടുപിടിക്കുന്നത്, ഇവിടെ നോർട്ടൺസ് കറണ്ട് ആണ് കണ്ടുപിടിക്കുന്നത്. അപ്പോൾ കറണ്ട് ആകുമ്പോൾ ഒരു ഷോർട്ട് സർക്യൂട്ട് പ്ലേസ് ചെയ്യണം, വോൾട്ടേജ് ആകുമ്പോൾ ഒരു ഓപ്പൺ സർക്യൂട്ടാണ് പ്ലേസ് ചെയ്യേണ്ടത്. ആ ഒരു ഡിഫറൻസ് മാത്രമേ ഇതിന് രണ്ടിനും ഉള്ളൂ. ഓക്കെ, ലെറ്റ് us do a problem. Determine the Nortons equivalent at terminals A and B of a circuit shown in the figure. And in the figure you can see that it contains a 20 volt battery and a 10 volt battery and 10 ohm resistor and 5 ohm resistor, and the terminals A and B are open, and you are asked to find out the Nortons equivalent circuit at the terminals A and B. So what is the first step? In the first step you have to find out Nortons current. Okay, before that you can draw the Nortons equivalent circuit as IN parallel to RN and the terminals A and B are open. And in the next step you can find out what is the value of IN, and also you can find out what is the value of RN. So first step is finding of IN. For finding out IN, we know that the terminals should be open circuited. Sorry, the terminals should be short circuited. Okay, so the terminals are A and B. Here in the question the terminals are A and B. We have to short circuit that terminals. So we will get a circuit diagram which is shown in the figure as like this. Here the terminals A and B is short circuited by placing a short circuit, and the current through that short circuit is IN, and there is 20 volt battery, 10 volt battery, 10 ohm resistance, 5 ohm resistance, and IN is placed in between A and B. So it will be short circuited and there will be a current, short circuit current IN, and we have to find out the value of that IN. See, here there are two loops. So in order to find out the value of IN we can use mesh analysis. Okay, see here the currents are marked as, in the first loop current is I1, that is in the clockwise direction, and in the second loop current is marked as I2, and that is in the anti-clockwise direction. You can see that in the direction of I1 and I2 you can see that the IN will be equal to I1 plus I2, right? So you can write that I1 will be equal to 20 divided by 10. Since I1 is flowing only through the loop containing 20 volt and 10 ohm, and I2 can be written as 10 divided by 5, and we are assuming that I2 is current that is flowing only through the loop that containing 10 and 5 ohm. So I2 will be equal to 10 by 5, that will be equal to IN will be equal to 4 ampere. That means Norton's current we have found out that like the value is 4 ampere. Next, what is the step? In the next step we can find out RN. For finding out RN, again we have to open circuit the terminals A and B. So the circuit diagram will look like this. That is, open circuit terminals A and B and remove the voltage sources by short circuit. So we will get the diagram like this. Okay, here the terminals A and B are open circuited and the resistance value is measured based on that point, and the voltage sources 20 volt and 10 volt are short circuited. So we will get a diagram like this. And in this circuit we can see that 10 ohm and 5 ohm are in parallel with each other. So we can find out RN as 10 into 5 by 15, that is equal to 3.33 ohm. So we got two values IN and RN. So then we can draw Norton's equivalent circuit, and which is Norton's current in parallel with Norton's resistance, that is 4 ampere is in parallel with 3.33 ohm resistance, and the terminals A and B are open circuited. Okay. So next we can do another problem. Find the current through the 5 ohm resistor. Here the circuit diagram contains 5 ohm resistor, that is at the right hand portion, and the voltage source are 5 volt sources, that is in 2 branches, and resistance are 2 ohm, 3 ohm and 2 ohm. So by using Norton's theorem we can find out the current through the 5 ohm resistance. And to find the Norton's equivalent circuit, for that we have to find out Norton's equivalent circuit. So first of all we have to replace 5 ohm resistance with short circuit. Okay, 5 ohm resistance can be considered as load resistance, and to find IN we have to replace it by a short circuit. So IN will be the current through that short circuit. So we can redraw the circuit diagram like this. Okay, here 5 ohm is replaced with a short circuit, and the short circuit current is marked as IN. And we can, for solving the value of IN, we can use mesh analysis. And here we are assuming that I1 is the current through the first mesh and I2 is the current through the second mesh. And here we want to find out the value of IN. And here we can see that IN will be equal to I2. So for solving the first loop, we can write the mesh equations by using KVL as 5 minus 2I1 minus 3 into I1 minus I2 minus 5 equal to 0. And by reducing that equation we will get 5I1 minus 3I2 equal to 0. That is the first equation. Similarly, for the second mesh we can write the equation as minus 2I2 plus 5 minus 3 into I2 minus I1 equal to 0. And by reducing that equation we will get a minus 3I1 plus 5I2 equal to 5. That is second equation. I am not going to the details of each and every step because I have, from the beginning class of mesh analysis, I have explained how can we write the equation for a mesh. So I think you are thorough with those steps. So I am not explaining those steps in detail. Okay. So equation 1 and 2 can be solved. See, equation 1 is 5I1 minus 3I2 equal to 0. Equation 2 is minus 3I1 plus 5I2 equal to 5. So equation 1 can be multiplied by 3 and equation 2 can be multiplied by 5, and you can solve the equations then again and you will get 16I2 equal to 25. Therefore I2 will be equal to 1.5625. So we got the value of I2 and we are interested to find out the value of IN. We know that IN will be equal to I2. So we got the value of IN. So Norton's current source value we got. And next, what is the step? We have to find out the Norton's resistance value Rn. For finding out the resistance value, we have to remove the load resistance 5 ohm by a short circuit. So the circuit diagram will look like this. To find Rn, open circuit 5 ohm. So we will get the circuit like this. Also we have to short circuit the voltage sources and current sources by open circuit. So we will get a circuit like this, and Rn can be found out by simple addition of 2 ohm with a parallel combination of 3 ohm and 2 ohm. So we will get Rn will be equal to 3.2 ohm. So we got the value of IN and Rn. So we can write the Norton's equivalent circuit as IN parallel to Rn. Here load resistance is also given, so we can draw the load resistance in parallel to Rn. So the Norton's equivalent circuit will contain 1.562 ampere is in parallel with 3.2 ohm, and also it is in parallel with 5 ohm resistance. So next we will go to the Norton's theorem for AC networks. And in the case of AC networks, the supply voltages and currents will be in AC form. So we will deal with the impedances of the branches, and we can do a problem. For the circuit shown in the figure, determine the Norton's equivalent circuit between the output terminals A and B. Here you can see that the input source is a voltage source that has a value 25 angle 0 degree volt, and resistance is 3 ohm, and there is an inductance J 4 ohm, and another resistance 4 ohm is in series with the capacitance minus J 5 ohm. So in the first step we can draw the impedance circuit by combining 3 ohm and 4J ohm. So the impedance circuit will look like this. The impedance circuit is, first of all we can draw the voltage source, and in the second case we can draw the first impedance as 3 plus 4J, and other impedances 4 minus 5j, and the terminals A and B are open circuited. And for applying the Norton's theorem, we know that first of all we have to place a short circuit between the terminals A and B. So the short circuit is placed here, and the current through the short circuit is IN. In the next step we have to find out the value of IN. For finding out IN, you can see that the current due to 25 angle 0 volt battery flows through 3 plus 4j and then through the short circuit, and it will not flow through 4 minus 5j, right? Because when current reaches the meeting point of 4 minus 5j and short circuit, current find a path which is which has lesser resistance, so it will flow through that path. See, short circuit offers lesser resistance to current, so it will pass through the short circuit. So the path 4 minus 5j is bypassed. So there will not be any flow of current through 4 minus 5j. So all the current that is from the 25 angle 0 volt battery, 0 degree volt battery will flow through short circuit. So short circuit current IN will be equal to, we can write by simple Ohm's law as short circuit current will be equal to voltage divided by impedance, that is equal to 25 angle 0 degree divided by 3 plus 4j. So we can solve that value by using calculator. So we will get IN will be equal to 5 angle minus 53.13 degree. Okay. Here I have on the right side I have written the method that I have used. 25 first divided by 5, and angles will be subtracted from each other. So we will get this value, and you can use calculator in order to solve this, or you can simply do by direct calculation. Okay. And in the first step we find IN. Next we have to find out Zn, and for finding out Zn we have to open circuit the terminals A and B, and also we have to replace the voltage sources by short circuit and current sources by open circuit. So we got the circuit diagram like this. So in this circuit 3 plus 4j and 4 minus 5j are in parallel. So Zn will be equal to 3 plus 4j into 4 minus 5j divided by 3 plus 4j plus 4 minus 5j. So we can solve that by using calculator, or any other method you can simply do yourself, and you will get the value of Zn as 4.53 angle 9.92 degree. So Norton's equivalent circuit can be drawn by using the Norton's current source IN and RN values. So that will be 5 angle minus 53.13 degrees in parallel with 4.53 angle 9.92 degree. That is a Norton's equivalent circuit. So this is the Norton's theorem for AC network, and you can use this theorem in order to find out the current through the unknown branch. This is all about this theorem.